In this video, we'll talk about how to do a simulation for sustainable groundwater resource management with THMC model. The study area is Taoyuan City, which lies in the northwestern part of Taiwan main island. This study underscores the crucial role of groundwater in Taoyuan's water supply, particularly in the face of frequent droughts due to climate change and reservoir sedimentation. As industrial and urban water demand increases, groundwater has become an indispensable alternative resource. THMC subsurface modeling software was developed to accurately simulate coupled flows in both saturated and unsaturated zones, allowing to address the unique hydrogeological complexities of regions like Taoyuan. By capturing detailed mechanisms of Taoyuan's low permeability laterite surface layer, THMC enhances the representation of infiltration processes. This advanced modeling capability supports informed water management strategies and promotes sustainable resource use in response to the challenges of climate change. First of all, how do we define our spatial domain for simulation? The boundary of simulation domain, shown in the figure on the right-hand side, basically follows the border of groundwater division of Taoyuan Zhongli Terrace, and we make a fine-tune to boundary of the east-southern area to make sure it follows the nature geographical features and watershed. Because the boundary in the west is in the offshore location, rather than exactly on the western coastal line, we need to know the slope around offshore area, and determine the elevation of each element along the coastal line. The second step, mesh generation. The mesh system is made up of triangular prism with around 37,000 nodes and almost 70,000 elements. With the help of THMC platform, we can create the mesh system based on the spatial domain much more efficiently. The third step, boundary conditions. In order to understand natural features and landscapes in the boundary area, we investigate regional topography, including river distribution and regional geology in Taoyuan area. Afterwards, we are able to define the boundary conditions. The coastal line in western boundary is considered to be Dirichlet boundary with total head equals 0, and others for no flux boundary. The fourth step, initial condition. Instead of obtaining the water level in each nodes by interpolation, we run a steady-state simulation to obtain the reasonable variation of water level. The biggest benefit of doing that is to avoid abrupt increase or decrease in water level. As the results shown on the right-hand side, the contours of water level basically follow the topography of Taoyuan Zhongli Terrace. The fifth step, hydraulic conductivity. We did a lot of work to collect borehole data and cross-section in geology as well. For some borehole data with pumping test conducted, we got to know the real K value for certain type of material, and at the same time, we refer to the table, which describe the relationship between material and K value. In Taoyuan City, we have 14 borehole data. And we were trying to create cross-section, which goes from northeast to southwest. In order to make sure for each cross-section, the elevation does not vary a lot, or too much, in terms of topography. Aside from that, we were doing analysis of land surface topography and soil material. Eventually, we can determine the distribution of K value, and there are in total 10 materials in this system. The fixed step, pumping data. Taoyuan is a really big industrial and commercial city in Taiwan, so we use a huge of groundwater for those purposes. The figure shows where the pumping well are located, and there are more than 1,400 wells in total. The annual amount of pumping falls in the range of 45 to 55 million tons. How do we digitalize pumping data is based on the XY coordinate and pumping depth of any pumping well. With the tool in our platform, we found the nearest node in the system. And in this point, the monthly pumping amount will be given in the input file. The last step, rainfall setting. There are 17 rainfall stations in the simulation area, and we divides the area into 17 subregions by applying Thiesen's polygon method in GIS. The rainfall data in each element is given on a daily basis. However, not all the precipitation can go into the aquifers and contribute to groundwater recharge. Because in reality, the surface is covered by different types of land use. If it goes with road and building, the element is supposed to be an impermeable element. We extracted road and building out of all the categories, shown in the green squares. With the tool and THMC platform, we can evaluate how many percentages of the green area account for in one element. If the majority of the area is road or building, then it will be defined as impermeable elements. After we define the spatial geometry in Geometry Mesh GUI, we start to set up the parameter values in Parameter Input GUI. This is the setting for parameters describing different types of materials, including hydraulic conductivity, or K value, which we just mentioned previously. And here is the place where we can set up initial condition, Dirichlet boundary, variable boundary, and point/source sink based on the data analysis from the field. Now let's get started on simulation. With the simulation results, we can conduct real-time water level predictions based on current conditions to provide scientific support for groundwater management. Furthermore, through forecasting and data analysis, we deliver accurate insights into water resource status, supporting decision-making for water rights issuance.